The goal of the next couple of lectures will be a description of what are the generators of a cyclic group. So assuming that the group G has a generator A, we want to find or have a description of all the generators of this group that is generated only by one element A. So the generator will be, of course, related to the single generator A here. Now, in this case, we're going to assume that this is finite order. So this description will be for the generators of cyclic groups that have finite order n for some natural number n. Now, we won't be able to achieve this goal in this lecture because this is a little bit of background we have to cover, but we will do it in the second lecture. So I'm going to start by looking at some proposition here. And the proposition here is going to tell me what are the elements of the group generated by A, by a single element A, when this element A has finite order. So assuming that you have a group, you have an element of order n, and here is a natural number. So this group generated by A, which remember is all the integer powers of A, that will be this collection. So it's going to be the identity, A to the first, A to the second, up to A to the n minus 1. So it's one less than the order of the element A. So let's look at the proof. Now, the idea for the proof of this proposition is the following. These are two sets. So the generator of the subgroup generated by A and this list of elements. So these are two sets. So to show that these two sets are the same, we're going to show that this set, the subgroup generated by A, is included in this list and the other way around. In general, this is what you do when you have two sets and you want to show that they are the same. So let me show you here. So if you have a set A and you want to show that is equal to the set B, this is equivalent to show that A is included in A and B is included in A. So you show both directions. That is what the plan here is. This set included in this one and the other way around. Now, one of these two cases is easier than the other one. So I'm going to start with the easy one here, which is B. Now, but before that, let's again look at the definition of what this collection is. So by definition, these are all the powers, integer powers of the element A. So all integer powers of A. This is the formal definition of this set. And we have proved already that that is a subgroup of a group. So it is a group itself. So I'm emphasizing that here. So that is this here contains all the integer powers of A, because that's exactly the definition, all integer powers of the element A. So if it contains all the integer powers of A, in particular, it's going to contain these powers. The identity is a power of A because it's A to the 0, and these are all powers of A. All these powers are contained in A, and this subgroup generated by A because this subgroup contains all integer powers. In particular, it contains this one. So we have proved this part B here. So this one is included in that. That is not difficult to see just by the definition of the group. The one that requires a little bit of work is to prove that this subgroup generated by A is included in this list. Now, remember, this is all the powers of A, integer powers. So we need to prove that it's actually equal to this one. So that's the one that requires a little bit of work. Now, how do you prove that this set is included in this one? What you need to do is this. You take an element here, and then you prove that that element is one of these elements there. So let's do that. So let's take an element X in this collection. Now, because it's in this collection, all the integer powers of A, that means that that element X is an integer power of A. So this is A to the M for some integer M in Z. So I'm going to call this number 1. Now, m here could be any integer. So this exponent does not necessarily have to be 1, 2, up to n minus 1. It could be 100n. So we need to show that we can write this as one of these powers. So that's the idea for the proof. So to do that, we're going to apply the division algorithm. And in this way, m for us is going to be the dividend, and n, which is the order of a, is going to be the divisor. So we're going to do this division, m divided by n. So if we apply the division algorithm, so we're going to obtain unique integers q and r, where q is the quotient and r is the remainder, so that m, which is the dividend, is equal to q times the divisor plus the remainder. I'm going to call that number 2. And r, the remainder, always is bigger than or equal to 0 and less than n, that is the divisor. So we're going to do this. We're going to take this expression number 2 and we're going to plug it into this one. So I'm going to replace m by q times n plus r. So that's what I say here. Replace 2 into 1. And we're going to obtain x is equal to a to the m, but I'm going to replace the m by q times n plus r. And in here, I'm going to use some properties of exponents for groups. So a to the qn plus r is the same as a to the qn star a to the r. That's laws of exponents, which are true in groups. Not all properties of exponents that you know from algebra, regular algebra, are true in groups, but these ones are. And this is also true in groups. A to the q times n is a to the n times q. Now, the reason we organize this like that is because we know that a to the n is the identity, and the reason for that is because we are assuming that the order of a is n. So a to the n here is the identity, so it's replaced here. So I say here because the order of a is n. And you have the identity to the integer power that gives you the identity. This a to the r remains the same all the way down. And the identity star anything is just the same element a to the r. What we have shown through all this sequence of equalities is that the element x, which initially was a to the m, is now a to the r. So that means x is a to the r. And then the important part here is what are the restrictions on the r here. So r here is between 0 or is 0 and is less than n. Now, r here is an integer. So we have an integer that is bigger than or equal to 0 and less than n. So that puts some restrictions on what r can be. So because r is an integer between 0 bigger than or equal to 0 and less than n, so the only possibilities for r will be 0, 1, 2, up to n minus 1. It cannot go up to n because it has to be strictly less than n. So r could be 0, 1, 2, up to n minus 1. Now, so that means x is equal to a to the r, and this exponent here is either 0, 1, 2, up to n minus 1. That means this expression here is in this list. So that proves that x is here. What we have shown is this, that this set is included in this one. Why? Because we took an element here, an m power of a, which could be any m, and we showed that that power has to be a to the r, where this r is either 0, 1, 2, up to n minus 1. So that concludes this inclusion. So we have both ways. We have two inclusions. So from this one, from parts A and B that we mentioned already, then we have that these two sets are the same, and that proves the proposition. All right. So let's go into corollary. So the corollary is gonna be simple because we already proved a proposition here. So this proof is gonna be short. So let me state what the corollary says. So in the corollary, so we have a group and we have an element of a group. That element, we call it A. And we're gonna assume that that element A has finite order. If that is the case, this is true. Now you have to read this carefully. On this left-hand side, this means the order of the element A. And on this right-hand side, that's the number of elements of this set. So these bars here mean something completely different here. This is order of an element in the group, and this on the right is the number of elements in this set here inside. So that's what we have to prove. All right, so let's go to the proof then. So let's assume that A has finite order, and let's just call that order, let's say n, with n here is a natural number. So the order of A is n is a natural number. Now, we're going to use, because it's a corollary, well, that means we're going to use the previous theorem. So let's do that. So by the previous theorem, we know that if an element A has order n, the subgroup generated by A would be this list. That's what we prove first. Now, but let's see. Let's count how many elements are here in this set. So let's look at this. Let me start counting from A. 1, 2, and so on. So counting means looking at the exponent here. So first element, second element, third element, n minus 1 element. Plus I have this element here. So I have 1, 2, 3, so on up to n minus 1. And then another one. So that means I have n elements here. So the number of elements in this set is n. But n is precisely the order of A, so that proves the corollary. So that corollary was not hard to prove because we already had the proposition at the beginning. Now, another corollary, which is also going to come from the theorems we proved already. And before I go into this corollary, let me remind you that all we're doing now, so the goal of this is to have a description of the generators of a cyclic group. So that's what all of this is going to go to. Of course, we're going to use some of these corollaries later and some other things, but the main goal will be that, to have a description of the generators of a cyclic group. So let's look at this other important corollary. So in this other corollary, we'll have again a group. We have an element of the group, and we're going to assume again that the order of that element is n. Now, if this happens, if any power k of A gives you the identity, then that means that the number n divides k. Now, let me explain this a little bit more. Now, we know that A to the n is the identity because we have this expression here, the order of A is n. So A to the n is the identity. What else could give me the identity? So what this corollary is saying is this. If you have any power of A that gives you the identity, this exponent here has to be divisible by n. There's no other way that you can get the identity with A, with that exponent, unless that exponent is divisible by n. All right, so let's look at this corollary. So let's assume the hypothesis. So we have that the order of A is n, and that A to the k is the identity. So we have order of A is n, A to the k is the identity. Let me call this one number 1. Now we also know that A to the 0 is the identity. This is actually by the definition of exponentiation that we are having for groups. So A to the 0 is the identity. So that means A to the k is the identity, and A to the 0 is the identity. So that means A to the k is exactly the same as A to the 0. So they're the same thing. Now remember, in the previous lecture, we proved, or we had a description on when two powers of A are the same. That depends on the exponents. Now in this case, k doesn't have to be 0. Remember, the exponents are not, if two powers of A are the same, the exponents are not necessarily the same, particularly when A has finite order. So if A has finite order, like this one, if you have two powers of A that are the same, then n, the order of A, has to divide the difference. So in this case, this k that is here is playing the role of I, and this 0 here is playing the role of j. So in the theorem that we proved in the first lecture, if two powers of A are equal, then the order of A divides the difference. So in this case, it would be k minus 0. That is that n divides k, and so that's why we hard to prove. Now let me give you a little bit of an example on why this is important, how this is going to be used. Now let's suppose you have an element of A that has order 3. Let's say an element of A has order 3. And for some reason you know that A to the k is the identity for some integer k. By the corollary, we just prove the order of A has to divide k. So 3 has to divide k. In this case, 3 has to divide k. That also means, or is equivalent to say, that k is a multiple of 3. So if you have that A cube is the identity, or the order of A is 3 here, that's what we are saying, then any power of A that gives you the identity must be a multiple of 3. That's because the order of A is 3. So let me emphasize that a little bit more. If the order of A is 3, A and A squared cannot be the identity, but A cube is the identity because the order of A is 3. Now, A to the 4 and A to the 5th cannot be the identity, and the reason for that is because of the corollary. If this was the identity, then this exponent must be divisible by 3, but it isn't. Same thing for 5. A to the 5th cannot be the identity because if it were, then this exponent will have to be divisible by 3. Now, A to the 6 is the identity. And how do you know that? Well, A to the 6 is A cube A squared. So if you think about why would that be the identity, the reason is by properties of exponents. You can write down A to the 6 as A cube A squared, and A cube is the identity, so it'll give you E squared, which is E. You can continue like this, and you can say, okay, so what happens with A to the 7th power? That cannot be the identity either, because if the order of A is 3, if this were the identity, it will have to be divisible by 3. Same for A to the 8, and so on. So the only way that a power of A could be the identity is if the exponent is a multiple of 3, assuming that the order of A is 3. So that gives us a nice description on when a power of an element will be the identity, knowing that you have the order of the element. All right. So the next two theorems that I'm going to state here, I'm not going to do a proof of them. There's a couple of reasons for that. One of the reasons is that the proofs are a little bit long to explain. That's one reason. And the other one is a little bit tedious to go through the proofs. So I don't think the proofs have like really nice ideas to be worth explaining here. Another reason also is because of the amount of time that is need to cover the material. So I'll rather just state the theorems without the proof. Now, if you're interested about the proof or where the proof is contained, I'm going to give you a reference later in the video. All right, so let's look at the first theorem without the proof. So the first theorem without proof is telling me this statement here, which I'm going to explain exactly what it means. I'm not going to give you the proof, but I'm going to tell you what it means. So if you have a group and you have an element A, which is order n, then let's say you want to look at the subgroup generated by A to the k, where k here is an integer. Now, this subgroup is exactly the same as this one when we take as exponent the GCD between n and k. Now, one of the advantages of having this description over this one is that usually this exponent is going to be less than k. So if you have a subgroup generated by A to the 200, for example, then usually you can have the same subgroup with another generator with that smaller exponent, which is usually desirable. So you always, for the most part, you want to have generators of a group where the exponents are usually small. Now, you cannot always do that, but you can hope for it using something like this. So that will be the first thing. So this is equal to that. And remember, the GCD here is the greatest common divisor. So we can replace the exponent k by the greatest common divisor between the order of a, which is n, and the exponent k that is here. As I said, that will usually reduce the exponent, which is something that you usually want. Now the second theorem, which is without a proof again, by the reasons I just explained, it goes like this. So again, we have a group, and we again have an element in the group G that has order n. Now this is going to tell me what is the order of a to the k. Now we already know that the order of a is n because it's here. So this theorem tells me what is the order of any power of a, knowing the power of the order of the base a. So if ak is a natural number, then the order of a to the k, this is order, is equal to this expression is n divided by the GCD, or the greatest common divisor between n and k, when n is the order of the element and k is this exponent. Now this here is a fraction, but actually this is going to give you a natural number. The reason this is going to give you a natural number is because the greatest common divisor between n and k is a divisor of n. So n divided by this divisor will be a whole number. It will give you a natural number, in fact. So I'm not going to do the proof of this theorem for the reasons I just mentioned earlier. Now, if you are curious about where the proof is, you can see the proof on page 80 of the book Contemporary Abstract Algebra by Joseph A. Gallian, and that's the 8th edition. In page 80, these two theorems that I just mentioned here, this one and this one, are both in one result. So I divided into theorems. In the book is only one theorem. So you can go ahead and check the proof there. All right. So let's continue with this. Okay, so let me do a little bit of, like, kind of give you an idea on why these two theorems are kind of important. Why do we want to use them? So the previous two theorems allow us to replace one of the generators for a more convenient one. That's what I was explaining there. So let me give you an example. So let's say you have a group and you have an element that has order 36. So what is the group? So just to think about an example of a group that has an element of order 36, could be, for example, Z72 and then the element 2, for example. So let's say you have a group and an element of order 36. And let's also say you want to have a more convenient generator for a to the 20th. So in this case, n would be 36, and this guy here, 20, that will be the k that we are referring in the theorems. So if we do that, then what would be a more convenient way to write a generator for this group? So it will be the same element a to a power, which is the greatest common divisor between n, the order of a, and 20, which is the exponent here. Now the GCD, or the greatest common divisor between 36 and 20, is 4. So a to the 4 also is a generator for this subgroup. So this is a smaller exponent. Let's say now you want to have another generator for a to the 25th, the subgroup generated by that element. Applying the theorem again, we can say that this subgroup, is exactly the same as the subgroup generated by A, the same base, to the greatest common divisor between n, which is 36, and k. In this case, k will be 25. Now, the greatest common divisor between these two numbers is 1. So it will be a to the first power. So that would be just a. So if you start taking powers of a to the 25, which is what this subgroup is exactly the same as taking powers of a. So you see the convenience in that. Taking powers of a to the 25 will give me bigger numbers, and it will be a little bit harder to write than just taking powers of a. So that's the convenience of the theorem. Let's look at this one, a to the 22. Let's say you want to have a generator, a more convenient generator for this one. Do the same thing. This is the same as a to the greatest common divisor between n, 36, and 22. The greatest common divisor between these two numbers is 2. So a generator for a to the 22 is the same, it is a square also. So let me emphasize that point a little bit more. Let me emphasize the idea with this example. So it is easier to list the elements of this subgroup represented in this way than this one. These two are the same subgroup. They represent the same. But it's easier to represent it like this than doing it like this. By representation, I mean put down the list of the elements. So let's say you want to find what this one is. So you start taking integer powers of a squared. So the first one will be a squared to the 0, which gives you the identity. A squared to the first gives you a squared to the second power, a to the fourth, and so on, until you get to a to the 34, and that is the last one, because if you go one more power, that will be a to the 36, and that will give you the identity again. And the reason for that is because a has order 36. Now these two sets again are the same, and this is the list. But if you try to represent it with this generator, so let's see what happens here. So you say a to the 22nd, start taking powers of this. The 0 power is the identity. The first power is a to the 22nd, and the second power is a to the 44. Now this number, a to the 44, now can be reduced a little bit, and let's see how. So you take a to the 44, and I'm gonna split it up in a way that it gives me a to the 36. So this can be split up as a to the 36 star a to the 8. And the reason for that is because just look at the properties of exponents in groups, which in this case, this property is correct. So 36 plus 8, that is 44. Now, the reason we split it like that is because a to the 36 we know is the identity because a has order 36. So then we can simplify all of this, let me write down here, as a to the 8 power. So this element here is a to the 8. A similar way you can do this. But you see here, in this way of making the list of the elements, I will have to simplify. So for the next one will be a squared, a to the 22 to the 3rd power. Then I'll have to simplify the exponent again using a trick similar to this one. That takes more work than actually just doing it like this. So in general, what you want to have is you want to have a smaller exponent because it allows you to write down the list of elements in an easier way, so you don't have to actually go through the simplification of this. So that's the idea, that's the application of the first theorem. Now the second theorem is this one. I didn't show you an example of this, and this is going to give us an idea on how to find the order of a k power of a if we know the power of the base. Now for that, I will give you some examples in the next video. So okay, so that's all I have to say for this video. Thank you for watching. Take care and good luck.